Hi everyone, long time no see, or rather, long time no monologue at my screen. This is the science update for Open Force Field, where we describe some of the major work that's been going on with science and force fields across the community. I think the last one of these that I did was in September, so today is actually going to be a bit of a longer one, covering basically the entirety of Q4 2025 up until now. This slide outlines some of the projects that I'll be talking about today. I did just want to start off by saying that Chris has joined us from the Kajara Lab. So he'll be here on a half-time basis, and he'll be working on science team and roadmap issues as they arise. We're really excited to have him here, and he's already been doing a lot of impressive work on Van der Waals terms. Otherwise, in this update, I'll be talking about a couple of major releases that we did over the past quarter, Sage 2.3 and the Rosemary Alpha, as well as ongoing protein force field work, give an update on QM datasets, talk a bit about the lipid force field work. This is probably not going to be in quite this order, and some of the progress that we've been making towards our next flagship force field update. Right. We're really excited to announce that Sage 2.3 has finally been fully released. It was released this past January, and it's now available in OpenFF Force Fields 2026.01.0. If you want to know more details about the fitting and benchmarking process of both Sage 2.3 and AshGC, our neural network charge model, those can be found on our preprint on ChemArchive. And we'll be hopefully submitting this manuscript soon. I know that members of the Advisory Board Committee and General OpenFF are likely quite familiar with Sage 2.3 at this point. But as this update is being recorded and will be uploaded to YouTube, I did just want to recap some of the major points behind the force field. So Sage 2.3 is the first OpenFF force field to be refit with a neural network charge model, which we've called AshGC. This is a graph convolutional neural network model that produces AIM1 BCC-like charges. With Sage 2.3, we've now refit all of the major parameter types within the force field, so valence terms, electrostatics terms, and Lennard-Jones terms. We've been wanting to move on to a neural network charge model for a while because of some fundamental downsides of QM-based charge methods. So these include complement dependence, for example, and poor scaling with molecular size. You can read more about our motivations in the preprint. That's not the only thing that's new about Sage 2.3 though. So when we refit Van der Waals parameters, to physical property data, we did update some parts of our workflow. And this took the form of three major steps. So firstly, we realized that some of the data in the ThermoML database was misentered. And some of the erroneous data was present in the Sage 2.0 fit. We identified as many data points as we could, largely through a somewhat manual method where we simulated a broad range of properties and then looked for points where the computed or simulated value diverged substantially from what was entered into the ThermoML database. Points with a high discrepancy we selected for checking against the papers, and then where there was a discrepancy between the paper and the value in the ThermoML database, we decided that was an incorrect data point. So that was step number one. A bit of a painful process, but invaluable, ensuring that the data that we were fitting to was broadly correct. Secondly, we realized that a lot of the properties in our training set actually required a bit longer equilibration than they were getting. And the way that manifested in the fit was we could get quite wildly diverging results for different replicates of the same property. In this case, shown is an enthalpy of mixing. And at this point, it's really adding more noise and signal to the fit. So we also incorporated a new workflow in Evaluator where we incorporated an initial or preliminary equilibration phase and used that to supply input structures to the actual stage where we compute properties. And that's called the pre-equilibrated simulation workflow. And you can see it results in properties with a much lower variance between replicates. Thirdly, in the process of diagnosing and fixing this, we realized that some of the properties we continued having trouble with had very viscous components. And we just couldn't get those properties to behave. So the third update to the workflow is that we removed high viscosity components from our training data. All of that resulted in the full Sage 2.3.0 force field, which we then benchmarked on a number of benchmarks ranging from QM to protein ligand binding free energies. The upshot is it generally improves slightly on Sage 2.2.1. So there is comparable performance with 2.2.1 and QM benchmarks. Some improvement on densities and enthalpies of mixing across the condensed phase properties. With the salvation for energies, 2.3 improves on hydration-free energies with water, but seems to worsen non-aqueous solvation-free energies very slightly. And on protein ligand binding for energies, it's fairly comparable with 2.2.1. Sage 2.3 also fixes specific problem cases, like the one shown here, where this ring, which should be planar, was rotating at 2.2.1. That's now successfully planar again in 2.3. So that's 2.3. It was a lot of work, and we're very glad to have it out there. Please do give it a try, and if you run into any issues, just let us know, and we'll do our best to fix it. Another big release that happened last quarter was the Rosemary Alpha Force Field, which was released in October. Again, I know the advisory committee has heard all about this, but just to recap for the YouTube recording, Open Force Field has been working towards a combined protein and small molecule force field for a while now, which we're codenaming Rosemary. And this Alpha Force Field is not going to be the final product, but is a major step towards it. We have several goals for this force field. Parameters that perform well both on proteins and small molecules. We plan to co-optimize these parameters to both small molecule and protein data. And we also want to achieve similar accuracy to existing protein force fields. And we've been using AMBER 14SB as our reference. And this project is being driven by a chip in Canada at the Gilson Lab. You might ask why we're so excited about this project when existing protein force fields already do quite well. Well, one reason is that combined with OpenFF infrastructure, it will streamline some kinds of workflows significantly. Currently, if we want to simulate a system like a protein with a covalently bound ligand or a post-translational modification, we have to go through this fairly tedious process of making sure that the force field can handle the modified residue. Once we have a new protein small molecule force field, in combination with AshGC, this should really become as easy to handle as any other small molecule. And actually, the hardest part will be reading in this PDB as a valid chemical graph. So onto the Rosemary Alpha itself. The Rosemary Alpha force field is trained to a few different data sets across 2 phases. In the first phase, the force field is trained to QM data, a combination of both small molecule and protein data, and a combination of optimized geometries and torsion energy profiles. And in this first stage, all the parameters are allowed to move. In phase 2, specific protein backbone torsion parameters are tuned to both GB3 backbone scalar couplings, as well as the fraction helicity of a 15-mer. The Rosemary Alpha was then put through a standard set of benchmarks that Chapin put together, which are organized into 4 tiers. These tiers increase with computational expense, and the idea is that a force field candidate should clear an earlier tier before progressing to the next one. On the tier 1 benchmarks, the Rosemary Alpha outperforms AMBER 14SB on QM torsion profiles and the scalar couplings of unstructured peptides in solution. Although that's actually true for Sage 2.1 itself as well, before fitting to additional protein data. The tier 2 benchmarks actually have to be split, as we took some of the targets in tier 2, the ones shown on this slide, and used them as training targets in phase 2 of training. So on the left-hand side, we have RMSD traces of the folded protein GB3 in long time scale simulations. And the idea with this, as with the other folded protein benchmarks that I'll show in a sec, is that the secondary structure should stay folded in simulation. With our Sage 2.1 force field and with many of our other force field candidates, we ran into this issue where the secondary structure of GB3 would unfold in simulation. Rosemary Alpha, on the other hand, successfully keeps the structure stable. On the right-hand side, we have another one of the training targets, which is the fractional helicity of this particular 15-mer peptide, AAQ-AA3. In gray are shown the experimentally measured helicities, and in this kind of olive green is the Rosemary Alpha. There's just been a slight color change here. And we can see, at least using the dihedrals and chemical shifts methods of calculating helicity, that the Rosemary Alpha firstly does fold the peptide into a helix, and secondly retains fractions of the helix that are much more similar to the experimental values than other force fields. Moving on to the other folded proteins that constitute the rest of the tier 2 benchmarks, however, Rosemary Alpha performs similarly to AMBER 14SB on BBTI and on ubiquitin, but seems to do a lot worse on hen egg white lysozyme. So for that reason, the Rosemary Alpha has not really progressed past tier 2 benchmarks, and Chapin is continuing to refine the force field. That being said, because we did put this out as a release candidate, we did start some of the tier 3 protein benchmarks for the Rosemary Alpha. So the tier 3 benchmarks, they include protein ligand binding for energies, as well as an additional 11 folded proteins in long time scale simulation. So we have results for the protein ligand binding for energy benchmarks, many thanks to Irfan Alibay at OpenFE, as well as the OpenFF infrastructure team for getting that done. And they show that the Rosemary Alpha performs comparably to FF14SB with the Sage 2.2.1 small molecule force field. We also ran long time scale simulations for these 11-folded proteins with Amber 14SB and the Rosemary Alpha and 2 different water models. And also many thanks to the Memorial Sloan Kettering Cancer Center for the use of their HPC time, these benchmarks. These have only just recently completed, so results will be coming soon, hopefully in the next update. In terms of next steps, as mentioned, Chapin is continuing with further fits to try and improve the performance of the protein force field candidate on tier 2 benchmarks. And one of the main directions he's exploring now is adding nuclear over-Hauser effect data for hen egg white lysozyme into the training set. He's already been through a few iterations of this. The first attempt reduced performance on the GB3 benchmark and unfolded beta hairpins, as well as increasing the helicity of the 15-mer. But reducing the weights of the AAQA3 benchmark seems to, target in the training set, seems to result in better performance overall. He's also experimenting with switching the loss function to use a logistic function, and this does result in improving the fraction of NOE violations in the resulting fits, but he's still continuing further fits along these lines. Another direction that Chapin may explore is starting to fit the epsilons of the MI backbones in case just tuning the torsions is not enough to get us where we want to be. And what this will likely look like is restarting his current fitting workflow, but from the Sage 2.3 force field. So that was the protein force field. Moving on to the lipid force field, this is another project that tries to expand the domain of applicability of OpenFF. The goal here is a force field that reproduces various membrane properties in simulation, with kind of the sub-goal as we get there, a force field that also reproduces various alkane properties in simulation. And this project is being driven by Julianne at the Scherz Lab. So Julianne started off with Sage 2.2.1. She ran some lipid benchmarks that I have previously presented, showing that 2.2.1 doesn't currently reproduce all membrane properties well in simulation. And in fact, when looking at alkane torsion profiles, they don't reproduce the minima of the torsion profiles either. Julianne tried refitting Sage 2.2.1 to an expanded dataset, incorporating additional alkane data to try and improve performance there, to no real effect in terms of improving the torsion energies. She therefore tried refitting to just alkanes to see if it was possible to even get there. And indeed, refitting just to a data set of alkanes and alkenes resulted in a near perfect match to the shape of the QM torsion energy profile. She then ran a further experiment where she started from the improved force field and expanded the training set back to incorporate general small molecule data, and found that starting from this new point, the energetic barriers of the torsion profile increased, but the correct minima was still retained. So this finding is very interesting, provokes some questions as to how we can best optimize the starting point of our parameters. Although it's, as we're planning to move to a new fitting workflow using SME, it's difficult to know how many of these findings, which are based on a force balance-based workflow, will translate. In terms of ongoing work, she has been co-optimizing van der Waals and valence terms, which has required some experimentation to find new good hyperparameters, such as the step size and truss radius that she's using for a fit. Moving on to datasets, there's been a lot going on, particularly in relation to our collaboration with Genentech and the Cadera Lab on the machine-learned organometallic force fields. So Jen has been creating and submitting a lot of organometallic datasets for various purposes, including one for benchmarking these compounds at a reference level of theory, one for exploring different multiplicities, as well as putting together a new dataset, which will get submitted as this gets assembled, designed to cover more diverse, complex structures than we currently have available in public databases. And as always, all of these datasets are openly available at the QC archive. Lastly, with Sage 2.3 out the door, we started working towards Sage 2.4. There's actually been a number of projects started across the team towards this goal, but the two major ones, or the two major ongoing ones, are on this slide. So firstly, we were looking at expanding van der Waals terms, and in particular, we're experimenting with adding an additional nitrogen van der Waals terms, which previous work on virtual sites, B-smarts, and looking at dispersion data has suggested would benefit our condensed phase properties. This is a project that was first started by Matt Thompson, but is now being driven by Chris Iacovella. Initial results suggest that it actually doesn't improve performance on condensed phase properties, but Chris is looking at a number of different things at the moment, including seeing if swapping the water model changes this conclusion. He's also looking at experimenting with fitting to different data. So for example, currently we select our enthalpy of mixing data at regular points, but it fails to capture the shape of the curve that enthalpies of mixing normally follow. So hopefully we'll see results on that in the next update as well. Jen has been doing valence parameter fitting with SME, where her cross-training project is kind of taking a bottom-up approach to automated smarts generation. So starting off with hyperspecific parameters, and then possibly clustering them. This is mostly an extension of what Finlay has done with specific torsion parameters, and extending that to bonds and angles. So initial results suggest that the automated bonds and angles do improve on the normal Sage fit to SPICE, but there are some kind of weird outlier results that mean that this is still ongoing work. So we're looking at whether we may need to tune hyperparameters, such as the learning rate, or whether we tune, say, the threshold of data availability for generating a new specific parameter. So that's some of the work that's been happening over the last quarter, and I'll just finish up by outlining some of the major focuses of Q1 2026 and how we plan to work towards them. So firstly, we'll continue with our current research projects, especially those working towards Sage 2.4, as well as working towards a protein force field. Other work relating to Sage 2.4, we plan to move our entire fitting pipeline over to SME, including the part where we fit van der Waals terms to condensed phase properties. And we plan to do that by creating this new package, DimSim, for handling and managing the distributed simulation of those said physical properties. And this is work that'll happen across both the science and infrastructure teams. The COG group has also been doing a lot of interesting work fitting force fields with SME and SPICE already, and we plan to assist there with benchmarking those force fields. We'll also continue assisting Chapin with his work, likely with benchmarks as needed as well. And we'll also need to determine the best approach to take once Chapin does have a protein force field candidate that he's happy with and passes protein benchmarks. In particular, how best to turn that protein force field candidate into a general force field candidate that passes both small molecule and protein benchmarks without losing the protein performance. In terms of collaborations, the collaboration with Genentech and the Kagera Lab has been renewed for another year, so we'll continue working on that project. And Jen has also recently started a new collaboration with OpenFE to create a new protein ligand benchmark repo. And of course, there's a lot of other work going around OpenFF. The lipid force field effort continues. The science team plans to refit a water model with force balance before we switch over to SME. And we plan to experiment with fitting to osmotic coefficients, which then requires implementation in DimSim, our new van der Waals fitting software. So lots going on, and hopefully you'll hear about some of this in the next update. Thank you very much for listening.